You who are maybe unfamiliar with TCAP, it stands for the Tritici Coordinated Agriculture Project, a large USDA-funded project. And along with that, we provide some of these webinar series. And today from UC Davis, we have Tyson and George who are going to update us on some of their experiences with Canopy Spectral Reflectance. They gave us a talk back in June, and so now we'll hear some of the latest updated information. So with that, Tyson, I guess I'll just turn it over to you.
Hear me? Okay.
I'll assume your mic is still working for you.
Okay. All right. So yeah, I'm not sure where George is. Hopefully he'll be in here
go
soon.
ahead.
But I'll just go ahead and start now. So what we're going to be talking about today is what we've learned and what we've improved upon as far as Canopy Spectral Reflectance goes from last year. There have been quite a few changes so far. So, all right, so just a brief outline of what I'm going to be talking about. I'm going to talk about some of the problems that we had last year. We're having low sensitivity in the 970 nanometer wavelength, which is our critical wavelength for all of our water indices. We're also having trouble collecting the data quickly and reliably with the JAZZ instrument just because of the software that's on there and a whole bunch of other things. I'm going to talk about some of the solutions that we had to the problems from last year. We think new gratings, new mirrors is going to solve our problem with the low sensitivity in the 970 nanometer wavelength. We wrote some scripts both for the computer and for running on the JAZZ that really help simplify things. I'm going to talk a little bit about both of those scripts, just what they do, how they help with everything. I'm going to talk about some of the results from these improved methods that we have now, some of the future improvements that we plan to make, and just some of our first impressions of the JAZZ versus the crop scan. We did get a crop scan here at Davis. We haven't really had a chance to get some good data with that yet, but we're hoping to be able to soon. But we do have some general first impressions already. So last year, we found that our spectrum that we were getting from our JAZZ was a lot different than what the spectra in the literature were looking like. So if you look at this graph here, this red line is more of what a typical spectra looks like from the literature. So ours mirrors it closely for most of it, but then right here around 930 nanometers, it just drops off. It's just a nosedive. And up here in this little yellow box is about where our key 970 nanometer wavelength is. And as you can see, there's a huge difference between what's in the literature from a regular spectrometer and what it's like down here with what we're seeing with the JAZZ. So this was a big problem for us. We weren't seeing a lot of variation in our 970 wavelength, which is where water absorbs. So that's the key wavelength that's telling us whether a plant is water stressed or not. And we knew it was off from the literature because the literature typically had values from negative 0.01 to negative 0.1. And the more negative the index is, the better. But from our JAZZ, we were getting values around negative 0.68. So this is clearly not consistent with what we're seeing in the literature. So we also did some other analysis on this, and we found that all of the variation that we're seeing, or at least most of the variation that we're seeing in the different indices, was due to this second correction wavelength it's supposed to vary along with the relative values of absorbance at the 970 wavelength, but it's independent of water. So it's basically supposed to correct based on biomass, because if you have a bigger plant with not very much water and you have a smaller plant with a lot of water, they may have the same the same absorption at this 970 wavelength, but obviously one plant has a better water status than the other one. So it seems like in my experiment last year, we were seeing highly significant differences using these water indices with this bad JAZZ setup. But I also have fairly large biomass differences between my two plants just because one is extremely drought sensitive. So we think that's what was going on there. A lot of groups said that they were having problems with collecting data in the field. It was very cumbersome to collect data from multiple channels in the field. Using the company supplied software, you have to push a whole bunch of buttons just to switch back and forth between them, and then once you finally started taking data, there was no way to mark it on the JAS when you began one plot and ended the plot. And we were taking several measurements per plot, so this was kind of a problem. You would have to go out in the field and write down which plot number was which measurement numbers, or you'd have to go and take blank readings in between them, and then you'd have to go on the computer later and pick them apart, and it was just, it took a lot of time to process things, and it was very easy. If you accidentally took 4 measurements for one plot instead of 3, it was really easy to just shift all of your data, so that was a big headache. A lot of groups were reporting that their JAS was overheating and it was just locking up and freezing. We didn't have too much of a problem with that here in Davis, but I don't think it was getting as hot here either. It did happen to us a few times though. A lot of people also, is very frustrating. Every time you turn the unit on, you have to set all these basic settings like the electric dark, the boxcar, the temperature correction, the stuff that should always be on, but you have to remember to do it every single time you turn it on. That was especially irritating when your JAS would freeze and you'd have to go put it in the cooler for 20 minutes or something to cool it down before you could use it again. So it just really slowed down the rate of data collection. There was also a bug with the JAS where it would save, if you were taking a reading from channel 1, it would also save readings from the other channels, but it would only do that sometimes, and usually the 2 channels were using different integration times, so then you would have a whole bunch of readings saved for one of your channels that were saturated and you didn't actually want those there, and that just made the post-processing even more complicated. So some solutions to some of these problems we had. As far as the sensitivity at the 970 nanometer wavelength, we looked at this graph here on the right from Ocean Optics, which basically just shows the sensitivity of the detector in the JAS. And way up here at our wavelength, there's very low sensitivity. It's around like less than 5% at 970 nanometers. So we thought this may have been what was causing that huge drop-off in that graph I showed you earlier compared to the regular spectrometers. And we looked at the gratings we were using. So this is basically the part of the spectrometer that takes a beam of light and it splits it up into all of its different wavelengths. So it's kind of like a prism. It spreads it out into like all the different colors. We were using this green one right here, which is grating number 4. And as you can see, it kind of goes up and peaks out around 800 nanometers, and then it starts dropping off. And over here around what we think is around 930 nanometers, there's a little bit more of a drop-off. So we're thinking that this, in combination with the lower detector sensitivity, was giving us that huge drop-off that we're seeing. So we talked with some of the engineers at Ocean Optics, and they suggested that we go with this other grating number 14, which is in orange over here. And we were hoping that even though we would lose some of these lower wavelengths that we have with the grating number 4, we would gain sensitivity up here in our important range. And because really we needed the 970 nanometer wavelength more than anything else. So it wasn't a huge deal if we lost some of the lower wavelengths, but there are some nitrogen related indices down in it.
Looks like we lost Tyson. He must be having some connection issues, so everybody just hang tight. He should hopefully be back in just a minute.
This is Dina from Nebraska. While we're waiting for Tyson to get logged back in, if you have any questions, feel free to go ahead and type them in the chat box, and we can have some discussions among those of us that are participating right now.
Welcome back, Tyson. Once you get your mic hooked up again.
We have a question from Jean-Luc too. So even if you get the right grading, it looks like the sensor has low sensitivity at 970 nanometer wavelength. Will it work? So maybe we'll start with that, Tyson, when you get a chance to get your... If you've just joined us, we're having some technical problems at Tyson's end, our speaker. So while he gets his microphone hooked up, we'll go ahead and continue. We do have a question on the floor from Jean-Luc, so if any of you have some comments or perspectives on that, feel free to go ahead and type in. Good to see you, Tyson. Is your mic working, or did that get lost when you got kicked out? No mic button. Oh.
Okay, it's back now. Can you guys hear me again?
Yep, we're good. Go for it, Tyson.
Okay. Sorry about that. Where did I drop off? What was the last thing you guys heard?
Now we do have a question, maybe we can start with that Jean-Luc has in the chat box there.
Okay.
And if you get the right
just
grading,
with Jean-Luc's question.
Yeah, maybe we start with that.
Yeah, so we were worried about that too. The question is, even if you get the right grading. Yes. So the question was, even if you have the right grading, it looks like the sensor has such a low sensitivity at 970 nanometers that it may still not work. Yeah, so this graph on the right over here is the relative sensitivity of the detector. So we were hoping that by choosing this grading number 14, because that has such a low transmission at these lower wavelengths where the detector has higher sensitivity, we could effectively increase the gain on the detector so that we would have, we would basically be maxing out these lower signals, and we'd be getting a little bit more sensitivity up here in the wavelength that we were looking at. So Also, 970 with the grading number 14 looks fine, but how do we deal with the low ranges to get other important indices? So basically, I'm talking mostly about the water groups. So we're the ones interested in 970. For the people doing nitrogen indices and that kind of thing, they're interested in the stuff that's much further down on here. So even with the grading number 4, they probably wouldn't be able to see much. They were using grading number 3, which is this red one right here. So they were using a completely different grading anyway. They shouldn't be having any of these problems. They're right in kind of like the sweet spot for where the detector and where the grading and everything works. So their stuff should be working pretty much just like any other spectrometer that's out there. Okay, it looks like Kieran's typing something. Maybe not. Okay. But basically, yeah, that was kind of what we were thinking. We're hoping we could get some more sensitivity in these higher wavelengths by going to this other grading. So if we look here, this is our new grading that we got here at UC Davis. So on the left over here is our grading number 4, our old one. And on the right over here is our new grading number 14. So I kind of tried to highlight where the 970 region was. So that's where this green bar is. So you can see on grading number 4 that we're having that problem where our spectrum just drops off and there's this really low sensitivity at 970 nanometers. But with this new grading number 14 that we got, it looks like the problem is fixed. So we have this nice signal up here. It's a little noisy, which is probably because it's in that upper region of where the detector doesn't have a very high sensitivity. So it's a little bit more noisy, but we can correct that by just taking more averages and kind of smoothing that out a little bit. But it did look like we had solved the problem until I talked to Jun Lee at Idaho, and he said that they had also got a grading number 14, and there were a couple differences between our two different setups, but they were mostly similar, and they both had the same grading. But his grading number 14 over here on the left looked pretty much just like his grading number 4. They both had this same drop-off problem, so it wasn't the grading that fixed the problem that we were having. It was something else that they changed at Ocean Optics on our spectrometers. So we went and looked through our purchasing orders, and we both had the same things, except the Idaho spectrometer, their grading number 14 had a different long pass filter, which basically what a long pass filter does is it blocks all wavelengths of light shorter than a certain wavelength. It's supposed to cut down on noise from there being too much light in the spectrometer. Basically, theirs had a lower cutoff, so it was letting in more light at lower wavelengths than ours was. And they also didn't have a collector, which basically just amplifies the signal that the detector is seeing. So you kind of have to be careful when you're putting that on. Typically, Ocean Optics doesn't recommend to us to put them on our channel that's facing up at the sky, the downwelling channel, but they do recommend that we put them on the upwelling channels, which are facing down at the plants, since those are getting less light. And our purchasing quotes said that they put upgraded mirrors in both of our spectrometers, but when we actually went and looked through on the actual JAZ unit, it appeared that they didn't have the upgraded mirrors, even though they had written down on the receipt that they did have the upgraded mirrors. So it could have been any one of those three things that was causing problems. But actually, on the forums, we found that the Minnesota group also got this grading number 14, and they had the detector on there, or the collection lens, and they also had the same long pass filter as we did here at Davis, but they did not have the upgraded mirrors. So we're really starting to think it was the upgraded mirrors that were causing the problem. So I went digging around on the Ocean Optics site, and I found this graph over here on the left, which shows the reflectivity of their upgraded silver mirrors. Their standard ones are aluminum coated. And as you can see, this has a very nice flat very high reflectance, around 100%, all through up from around like 450 nanometers all the way up through past 1,000, which is beyond what our detector can even see. But I wasn't able to find anything of what their standard mirrors look like. So I kind of went digging around on Google, and I eventually came across this graph here on the right, which shows, this is from Perkin-Elmer, so it's a different company, but I'm thinking that the mirrors are generally similar. So they have this red line, which is their silver mirror, and it looks very close to what the Ocean Optics one does. It's maybe a little bit more smoothed over. Maybe it's just kind of a representation instead of actual data collected from the mirror. But they have the silver one here, and they also have an aluminum one, which is the basic mirror that Ocean Optics uses. And shockingly enough, it does have this drop-off in reflectivity right around 900, 930 nanometers, where we were seeing problems with ours. So it looks like the drop-off problem that we're seeing may actually be due to the mirrors. And I don't know why at Ocean Optics they didn't let us know about this, or they didn't know about this, or whatever. But the Idaho group, from what I understand, has a grading number 4 and a grading number 14, both of which they sent back to get the upgraded mirrors installed. So hopefully in the next week or so, they'll be getting that back, and then we'll be able to see if we can still use this grading number 4 and get our valid 970 nanometer wavelength readings. I think Junli's typing something right now. He's actually the one that was telling me that they're getting the new mirrors on these 2 different channels. So hopefully when they get theirs back, we'll be able to have one set spectrometer set up that everyone can get for water that we know works, and everything will be happy. So yeah, their JAZ is coming back tomorrow, and I don't know if any of you have seen the forum that we have on the Plant Breeding Training Network, but pretty much everything I'm saying in here today, and also some other stuff and instructions on how to use the new programs and everything is on there. So Junli will be updating on there, and he'll let us all know what the spectra look like when he gets his JAZ back with those new mirrors and the 2 different gradings. So some of the other solutions that we had to our problems from last year were we wrote several scripts. We wrote one that runs on the JAZ. It's this JSL script. JSL is just the JAZ scripting language. So this script made it so that it was much, much easier to use the JAZ in the field. And we also found a new method that improves the reproducibility of the data that we're collecting in the field. So we have less variation when measuring the same plot than we did before. So statistically, that helps us out a lot. And we also wrote another Perl script which simplifies the post-processing of the JAZ data. So it makes things a lot easier after you actually get back from the field and you want to start looking at the differences you have. So for the JSL script, we had a nice one that would take three-point measurements within a plot, and then we could go like average them together and get the number for the plot. But as we were starting to analyze their data, we found that when we were using this 3-spot sampling method, the variation within the plots, so at those 3 different spots, was almost as great as the variation was between plots of different genotypes. So this was a pretty big problem. So we set up an experiment where we took 3 measurements at each of 3 locations in a plot for 3 different plots. So we're taking 9 measurements at 3 different locations in 3 different plots. So just kind of visually, this is what it looks like. So we had 3 plots, plot 1, plot 2, plot 3. And then within each one of those plots, we took measurements at 3 locations. We took 3 measurements at each location there. So what did that look like? On the left over here, there's some Excel graphs, and basically this is a comparison of the NDVI values, which is a biomass index we were using this instead of water, just because this was early in the season before there was any water stress at all, but we were seeing biomass differences. So the three different graphs are basically just image 1 in spot 1 versus image 2 in spot 1, and the next one, and that's for all three of the different plots. And then the second graph is like image 1 versus image 3 at spot 1, and then image 1 versus image 3 at spot 2. So as you can see, there was a very high correlation between the different measurements at the same location. So this is basically showing us the variation that we're getting with the jazz that's due either to something inherent with the jazz, or with the wind blowing, or with the time, if clouds are coming, or anything like that. So this is just kind of giving us an idea of the best possible reproducibility we could be getting with the jazz. And over here on the right, this is showing us the variation between or within the plot. So we averaged these three. So we took each of these three measurements at each of these spots. So we averaged together all three of the measurements at spot 1 and plot 1, averaged together all three of the measurements at spot 2 and plot 1, and so on and so on. And then we compared those together. So we compared, so this graph up here, for example, is for plot 1, we compared the first spot with the second spot, and then for plot 2, we compared the first spot to the second spot. And as you can see, there was not a very high correlation between the different locations in the plot, even though at that location we're getting a very high reproducibility. So it seems like the jazz instrument is recording faithfully. It's giving us really reproducible results. The wind isn't affecting it that much. This is actually a pretty windy day, but at the different locations in the plot, we're getting hugely different numbers. And up here on the top, this is just kind of to give you an idea of the variation between the different plots. So this is when we average together all of those different spots. And I have on here the standard deviations, but this next slide is better for looking at those. So we were actually able to solve this problem of huge variability by developing a new method of recording the plots. So instead of taking several point measurements throughout the plot, we decided that we would try and scan along the plot. We actually thought of doing this because we just got a new project scientist from Italy, Marco Macaferi, and he had been using the Green Seeker, and that's basically, it basically just records NDVI, but you just hold it in your hand and you just kind of walk along the plot, or you can put it on the back of a tractor and just drive over your field, and it'll give you all of your measurements, but it's going along there scanning. So we tried to do something kind of like that. So we took our script that we had and we modified it so that it would take 800 samples at a time. So we would basically just start measuring, and then we would slowly walk along the plot, integrating. So we're taking 800 pictures of this plot, and then at the end of it, they're all getting averaged together and saved as one value for the plot. So when we looked at that, this table is just a comparison of the point method here on the left, which is where we're taking 3 distinct measurements per plot. And on the right is the scanning method. So it's a little weird to look at, but basically I have the standard deviation of each one of the different plots here. And you can see that they vary a little bit over here on the point method. And this fourth value that I have here is the standard deviation. So just kind of a measure of the variation between the different plots. And if we compare so what I did to get an idea of just kind of how much we could see the differences in these plots, I took the standard deviation between the plots. So theoretically, this should be the largest standard deviation that we're going to get from different genotypes. You would expect that you would have bigger differences between different genotypes than you would within one plot, all of the same genotype. So basically this number 1.85 is telling us that there's 1.9 about times more variation between different plots than there is within a plot. So that's not very good. I mean, there's still more variability between the different plots than there is within plots, but it's not a very good number. So over here, if we look at the scanning method, first of all, you can see right off the bat that the standard deviation with this method is much lower for recording the same plots. And these are the exact same plots that were measured with this point method over here. So it's not like one of them had a lot of lodging or big holes in it or anything. These are the exact same plots. So we have much lower standard deviation within the plots, and we also had much lower standard deviation between the plots. So we were worried that maybe we're just kind of getting one value every time we go over these, even if they're not very different. But when we look at this other number, this ratio between the within plot and between plot variation, we see that there's 6.8 times about the amount of variation between different plots as there is within plots. So it looks like we did solve our problem of reproducibility here. We can have a lot more confidence in separating our genotypes with respect to, in this case, NDVI, so biomass. But it is also increased the reproducibility that we have for looking at the other indices too. So to do this new scanning method, we had to kind of build a new pole. We had like a really nice adjustable aluminum pole that we're using for the point measurement method, but it was just kind of big and hard to carry around because you have to be holding this up. You can't be dragging it on the ground or it's going to be kind of bouncing all over the place. So we made kind of this lightweight pole out of PVC, and we just have little strips of foam basically holding the fiber optics into place in here. We have, it's kind of hard to see in this picture, but we have little PVC caps that we put on the end of here. So when we're taking the dark reference or when we're moving it back and forth from the field, we can put these caps on to protect the fiber optics so that they don't break. And then down here you can see we have the caps off, so the fiber optics just kind of stick out a little bit, and you can make sure they're straight, and you can just start scanning along your plot with this. And we also have a post level on here. This is basically just so that we're making sure we're holding it straight, so we're not integrating like the plot next to us or like your shoes or something if you're tilting it too much one way or the other. One thing that we would like to do in the future is to have a way to kind of anchor this pole to your body somehow so that you're not holding it up with your arms. As you can see, we have these little orange tape markings on here. These are basically just distance markings. So right now we're using this one, I believe, which is 60 centimeters. So if the top of the canopy is at this tape marking, it's 60 centimeters from the end of the fiber optic. So you just kind of hold it there, and at least with some of the plants we have here within a field, there's a huge amount of variation in the height. So it gets kind of irritating when you have to keep holding your arms up really high or putting them down really low for each plot. So it does get kind of tiring carrying this thing around. So it'd be nice to find a problem or a way to solve that problem in the future. So some of the problems I mentioned earlier that we were having with the jazz, we think we solved most of them with this new JSL script. So Kieran has a comment over here. While moving the pole over the plot, I felt it was difficult to keep the bubble level center, which indicates that the sensor is in the correct position. So yeah, it is a little hard when you're walking along the plot to keep the pole perfectly level, just because you're walking, you're kind of bobbing up and down, back and forth. But as long as you keep keep this bubble just basically somewhere where you can see it so that it's not pegged all the way to one side. We found that we went through and we did some tests where we walked very carefully and made sure that it was perfectly level the whole way, and then we walked through and kind of a little bit rougher, and so long as you weren't going it was still giving us reproducible results. So it's not of absolute utmost critical importance that it's perfectly level, but it is important to keep it generally level.
May I make a comment, Tyson?
Yeah.
Yeah, I think that the critical thing is you need to understand that when you are taking 400 subsamples, even if a few of those samples will not be perfectly vertical, it will not affect you that much. But what is important is that with this huge number of subsamples, you are dealing with the heterogeneity of the surface that we are measuring. We're not measuring just a painted wall or something like that. We are measuring leaves that are moving, that have spaces in between, spikes that are coming out. So it's a very heterogeneous surface that introduces a lot of variability within. So I think that this is pretty important to have, to increase the number of subsamples from 3 to the hundreds, gives you a lot more precision in every individual measurement. And that precision is the one that will give you the power to detect your difference between the genotypes. That number that Tyson showed, a difference between 1 and 6 or 7, these are the F values of your ANOVAs, because it's the variation between versus the variation within. So you have a lot more power to detect differences with the scanning method. So I will really encourage the group to start switching to that method. That it has in addition an additional advantage is that at the end of the plot you have a single spectrum. You don't need to do any post-processing of averaging the 3 spots, and so I think it's a lot cleaner, and we can take advantage. The luxury of having hundreds of samples is something that you can usually not afford, but here in 4 seconds you can have all these samples, and the equipment has the power to integrate them very fast. So I think that we can increase the precision of our analysis significantly by switching to this method. So I would say that of all the things that we want to say today, the most important one is the switching to the point method to the scanning method. And we are open to discuss any questions or concerns that you have about this method. Tyson, there's a question from David. Can you answer it?
So Dave asked a question, is there a way on the Jazz to change it from the snap mode, so basically this point measurement mode, to the scanning mode? There kind of is. You can do this with their regular program that they have on there. Basically all we did to make it a scanning mode instead of kind of a picture mode was we increased the number of averages. So depending on your integration time, it's going to take a certain amount of time to take so many images. So typically we use an integration time of 0.003 seconds, so 3 milliseconds. So it takes that long to take one picture. Before we were taking something like 10 or 15 images per picture, so per point measurement. But we decided we'll just increase this to a ridiculously high number so that it takes something like 4 seconds, 7 seconds to actually take that many measurements. And when the Jazz is done taking all those consecutive measurements, it saves them into just one file. It averages them all together and then saves them as one value. So that's basically all we're doing with the scan mode. So you could do that with the regular program that we have on there. And we also wrote another JSL script that we actually modified into this scanning script that you can actually mark where a plot starts, and then you can make several measurements, and then you can mark where the plot ends, and then later you can go back and average those together. But as George was saying, we think it's a lot better to take the extra number of subsamples. So right now we're taking 400 subsamples, as opposed to before we were taking something like 30 for an entire plot. So we are getting
I think that
much
there
better
may still
results
be,
with the
I
scanning
think it
method.
might be still an overkill. The 400.
Okay,
So
so Karen says,
probably we have a little bit of
yeah.
study to do. Maybe 100 samples or 200 would be enough, but we haven't established that completely. I think that Tyson, you did your experiment, your real experiment with 100 samples.
Yeah, so I'm going to talk about that later a little bit, actually.
Okay.
Right now we're doing 400 for all of our plots, but actually on my own experiment, I was doing 100 averages, and I was still getting significant differences. So yeah, I'll talk about that in a little bit. And we are also planning, we've been planning to do it for a while, but it keeps raining, and then there's wind, and then there's cloudy days, and we just haven't really had a chance to go out and take a bunch of measurements with the crop scan and do all of the tests that we want to do with our jazz to find out just kind of what the sweet spot is for the number of averages to take, so that we can take the measurements as fast as possible, but still reduce the variability. Catherine says, the Remote Sensing Institute that we have been working with here at University of Nebraska has expressed concern about light reflecting from your body and affecting your measurement when you walk along the plot. When you take a point sample, you can avoid that reflectance much more. Have you had any issue with this? Well, I think that the data kind of speaks for itself, what I showed you earlier, where we're having much more variation between the plots than we were within the plots. So even if we are getting a little bit more reflection off of ourselves from walking around and moving, the advantage that we're getting from integrating the whole plot is just overwhelming any amount of noise that we could be introducing into there. Additionally, we do try to just kind of wear the same kind of clothes. Like I have a set of field clothes that I wear every time I go out there. So, and also within a day, you're going to be wearing the same clothes. So any amount of light reflecting off of you should be generally the same throughout the day. It may change a little bit as the sun moves through the sky, but we always try to stay on the far side, like the shadowed side of the plot, so that we're not casting a shadow onto the plants. So I don't think we're having too much of a problem with light reflecting off of ourselves. If you are worried about that, I was reading through some of the crop scan stuff. They recommend that you wear dark clothing just so that if there's light hitting you, it'll get absorbed by your clothes instead of being reflected back onto your plots and messing with your measurements that way.
So we should buy black shirts for...
So David's typing a question. I'll just kind of go until he's done with that. So addressing some of those problems that we were having last year, as far as it being cumbersome and time-consuming to switch between measurements with the jazz, we don't have that problem anymore. The script that we have automatically switches between the different channels. So right now we have 3 channels. We have 2 upwelling channels that are facing the plants, and then 1 downwelling channel which is facing the sky. And you just push one button, and then the script will automatically just switch between all those channels. They can all have their own separate integration times, so all that is solved. We were having problems before when we were doing the point method because there was no way to make a distinction between where one plot began and where it ended and where the next one began. We don't have that problem anymore with the scanning method because we're only saving basically 1 measurement per plot. So if you happen to accidentally push a button when you're walking between plots and you measure the soil in between them instead of the actual plot, there's a menu with the script that you can go in there and you can actually set back the counter, the file counter one, and you'll basically just overwrite that bad data that you just took. So that's not a problem anymore either. The basic settings that you have to set every time, like the electric arc, the boxcar, the temperature correction, the script automatically sets these, so you don't have to worry about remembering to do that anymore. We don't have that same bug in our script that the the default Jazz software has, where it saves kind of these ghost spectra where you're recording with channel 1, but it's saving files for channel 1 and channel 2 at the same time, but one of them's saturated because they have different integration times. So we don't have that problem anymore. And as far as the Jazz overheating and freezing, we haven't had that happen a single time so far with this script that we're using. But on the other hand, it hasn't been very warm here in Davis. It's been below 85 degrees every time we've used it. And we didn't have as much of a problem with it freezing last year as some of the other groups did. So it could be that some of you may still have problems with that. It may just be inherent with the system. But so far, it seems that running these scripts is doing a better job of not killing the Jazz than the program that we were using before. So David says that in the little he's used this, the lower wavelengths were more closely estimated. The longer wavelengths showed scatter and high error. So yeah, it's kind of what I showed way back up in the presentation with our new grading number 14. There was a lot more noise in the upper wavelengths with our new one. So there are differences over time in quality of light, and as sun estimate changes, getting over the whole set in an instant in time would be better than a long period on each day. Wind can be moving. Okay, yeah. So yeah, we haven't seen too much of a problem with the wind. We initially found this that we were having this huge variation with the point measurement method because it was a really, really windy day in Davis, and we came back and we weren't sure if the wind would affect it, and we started looking at our data, and there was huge variation within a plot. And at first we thought it was the wind, but then we went out and did those experiments that I talked about, and we found out that it was actually just the heterogeneity in the plot. And as far as the longer wavelengths, just kind of having more noise. Yeah, they do have a little bit more noise, as I showed you. It kind of goes away the more averages you take. So since we're taking such a huge number of averages, not only is it taking care of kind of the heterogeneity within a plot, it's also taking care of the random noise that the actual Jazz is creating. It's probably due to the low detector sensitivity up in those upper wavelengths that's making it just kind of go crazy up there. But the more averages you have, the closer you get to the true value. So both for the plot and just kind of in general for those upper wavelengths. But as I'm going to show you later, we have that noisier region, but it doesn't seem like it's too much of a problem. So we also wrote a Perl script that we have to help post-process our stuff after we get out of the field. So this program, you just run it on your computer back in the office. Uh-oh. What just happened? Okay, that's interesting. Okay, so anyway, you just start this program up on your computer back in the office, and you transfer all of your Jazz data off of your SD card. And this program will take output from this new scanning method. It will also take output from, if there's somebody that still wants to do this point measurement method, we have a program that will do that, and you can set dividers in between the different plots. Basically, when you run the program, it will condense all the readings from all the plots, and if you're using that older method, it will average together all of the different readings from a single plot, and it'll put all that information into a single tab delimited file so that you don't have these hundreds of different files that you have to go through and open up in Excel and combine them together and stuff before you actually have any useful data. So this one tab delimited file is really easy to work with in Excel, and if we want to, we can actually write a macro so that basically you run this Perl script, then you open this in Excel, and you just hit another button, and you have all your indices right away. So this is a little hard to see. maybe. But basically, this is that tab delimited file that I'm talking about. So in one column, you have all of your wavelengths, and then each of these other columns is a different plot. So this is plot 1, this is plot 2, plot 3, so on and so on. So we have all of the different wavelength values for all of our different plots in one Excel file. So what you can do is just open up a new tab in Excel, and you can basically just put in a formula that is basically just averaging something, and then you go back to your initial sheet with the huge list of all of your wavelengths, and you just grab the wavelengths that you want to average together, and you hit enter, and then it'll calculate it on this other sheet, and then you basically just do that for each of the wavelengths that you want, and then you can just take that formula and drag it down, and it'll basically just calculate all of those for you, and then on that same sheet you can put in any indices that you want. So here we have 2 water indices and NDVI. Basically those are just calculated using these other wavelengths. So you just put these in as formulas, and you just click and drag all the formulas over, and then you have all of your indices for all of your plots within less than 5 minutes. For probably overkill. It currently takes us about 30 seconds per plot, but we're taking information from 3 different channels. We're taking with grading number 4, grading number 14, and also a downwelling channel. So for those of you that are using only 2 channels, so just one upwelling, one downwelling, you can probably cut that time down to around 18 seconds, still using 400 averages. So it's a lot faster. Junli asked if we're using the downwelling data now. We aren't right now, just because the bulk of our data that we're analyzing is from our new bench with grading number 14 and the upgraded mirrors and everything. And the downwelling channel that we have is the old grading number 4 that has that drop-off problem. So it's kind of hard to correlate changes in the 970 wavelength in that in that old spectrometer setup to the new one that's actually working properly. So
may I make a comment?
Yeah.
I just want to make a comment that why in our particular case it's not that important, but it turned out to be more important in the association mapping panels. We only have 4 genotypes, so we basically measure them in a very short period of a few minutes. We have 4 measurements, and then we have 20 blocks. So the blocks are taking care, and we use the blocks as part of the analysis of variance. So the blocks are taking care for us of the variation in sound changes during the day, because we have that luxury. When you do an association mapping panel, where you will need to be hours taking measurements, and you will be at different strengths of the sound, probably at that time we will need to consider using those upwelling channels. But for this particular project, we didn't have the need to do it. But I think that we need to start looking at that a little bit more seriously when we want to do the association mapping. It won't be that easy to do, because we did some measurements last year, and what we found is that there was not clear correlations between the changes you get in the one that looks up is the downwelling channel. Sometimes we saw, for example, in some point we saw a very short cloud, so there was a big decrease there. But then when we look at the reflection for the plant, there was no change at that point. So if we would have made a correction there, then we would have changed all the values of the observations, where in reality there was not a big effect on the Canopy Spectral Reflectance. So I think we need to do a little bit more of research on the downwelling data if we want to use it, and also we will need to have it with the correct mirrors and correct gratings, so we can do the corrections that we need to do. We also need to wait a little bit until we get the results from Idaho of the the new mirrors, because it might be that the grating number 4 with the correct silver mirror will give us all what we need. So if that is the case, maybe we can all go to a 2 spectrophotometer channels, one up, one down in grating 4 with the correct mirrors and solve all the problems. But I cannot give you that answer now. We need to wait until we have the data of how the grating 4 with the silver mirrors looks like. So I'm returning back to Tyson.
Okay, one other thing I'd like to add to what George said is that last year when we were seeing that there were differences in the downwelling channel, but we weren't seeing those reflected in the upwelling channel, is that we were taking those measurements, we were taking the upwelling channel, the downwelling channel, so the one looking at the sky, at the end of each plot, rather than now we're taking all of the measurements at the same time, basically. So it could have been that a cloud did pass when we were taking the downwelling measurement and the cloud was not present when we were doing the actual measurements on the plot. And also that analysis was done with the old grading, which had low sensitivity in the 970 nanometer wavelength. So we may not have been seeing the full effect of clouds and things like that. So as we were saying, we still need to do more testing with that. Hopefully when the Idaho group gets their new jazz, we can get everything set up so that we have the same upwelling, downwelling spectrometer setups, and then we'll be able to more definitively say whether or not using the downwelling as a covariable for the upwelling is actually worth doing. Okay, so yeah, so in the future, we'd like to find the optimal number of averages, and also if any of you have suggestions or things that you'd like to see change, extra features, just let us know on the forum so that we can make those changes. I won't know unless you tell me. We're kind of incorporating everything we can think of right now, but we could be missing things, and if other groups are doing slightly different things, it might be better to just write the program slightly differently. So David has another comment over here. He says the shorter wavelengths have different values over time, but the 900 nanometer has no difference over time. So this means the water band values are less related to differences in the sun and probably more water situation in the canopy, which holds more constant over time. I was curious over these differences, but it makes sense since it's due to water status. So yeah, also the yeah, I don't know what data you looked at, but the 900 nanometer is if there's no difference over time. So that's the one that's used as a correction. That's not actually where the water is absorbing. So I would imagine that the 970 nanometer wavelength probably wouldn't change too much unless there's clouds and things going over. Yeah. So yeah, we're gonna run some more tests just to see how things are changing throughout the day, how they're changing with clouds. I did do one experiment on a cloudy day, just kind of taking one genotype over and over, and there were huge differences on the water status of the plants based on whether a cloud was there or not. So now that we do have the properly functioning 970 nanometer wavelength, we are seeing big differences if there are clouds or not. So we have to be a lot more careful about that when we're doing water indices. As for the nitrogen people, I'm not sure how much clouds affect that. You may be able to actually correct for that better than people doing water indices, but we'll have to do tests on that to see for sure. Some other feature improvements we'd like to make for the Perl script, we'd like to further streamline it. Right now, you need to have in the folder with all of your JAWS files, basically a file for each channel that lists the wavelengths for that spectrometer. So you have to set that up once before you run it, and then you can always just use those same ones, but it's kind of a pain to do in the first place. So we'd like to get rid of that. And also right now, you have to run it once for each channel. So we have 3 channels, so we're running the program 3 times. it only takes usually less than a minute to run it each time, so it's not a big deal. But in the future, we'd like to make it so that you just run the program once and it processes everything for you and outputs it all at once. We also may be able to do automatic calculation of indices. We can do this either with a Perl script or maybe with a macro in Excel. But to do this, we're going to need to decide, this kind of as a group, what boxcar or bandwidth range we want to use. So far, I've been using the center wavelength. So, for example, if I'm calculating the reflectance values for 970 nanometers, I will go look at all of the different wavelengths that we have. I will pick the one closest to 970 nanometers, and then I will pick the 5 wavelengths above that and the 5 wavelengths below that, and I will average all those together and use that as the one value for 970. So we may want to look into that and see just kind of what the optimal boxcar width is that we want to use for all of our indices. It may end up being different for the different indices. So a water index versus a nitrogen index or a biomass index may be different. So we need to look into that. And we also need to decide on a set of indices that we want to use if we're going to program this into something. Everything that we're doing right now, we are putting on a forum at the Plant Breeding Training Network. There's a Canopy Spectral Reflectance forum. Here's the address for it. If any of you haven't been there, I'd recommend going there and checking that out. I posted up basically everything we found, things we're worried about, any new scripts we write and put up there. So there's a lot of good stuff there. And you guys can also go there, and if you find a bug in one of the programs, let me know and we can fix it. If you have any feature requests, and also people can put up just kind of tips and tricks that they find. For example, Sharon earlier said he was only doing 100 averages for all of his plots, so he may be able to, if you're wanting to do fewer averages, you can talk to him, maybe find out kind of what the variation looks like in that, to see if it's something that you'd also like to do. So for the crop scan versus the JAS, as I said, we don't really have a good data set to compare between the two. We went out there once and took measurements for the whole day, and we got back to the lab and we found out that it was incorrectly configured, so it decided not to save any of the wavelengths. So we still haven't had a chance to get back out there and do that again. But right off the bat, that kind of shows you that it's a little bit more difficult to work with. You don't have the instant feedback. And just for us, we haven't been working with it as much, so that could also be part of the problem. But the software is pretty antiquated and difficult to use. Here's just kind of a screenshot of it. It basically runs in the command line, and you have to be careful with it. For example, if you try to close a program by clicking this X button that you usually used to clicking, it'll crash your computer. You have to actually hit the escape key to end it, otherwise you're gonna lose everything you were working on. So over in the comment box, Shelnug says, I'm very interested in what decisions get made on standard indices and how they are calculated. T3 at the moment has no CSR data, and we need some sort of this information to be able to upload CSR data. So yeah, really the sooner we can decide on what indices to use, what boxcar to use, it'll just be better for everybody, streamlining their data processing and also for uploading it to T3 so that we have one standardized.
Know how to set up so maybe what we can put, what are the settings that we are using. A car box of 5 is that we're using right now. So if anybody has any problem with that one, we can discuss it. If not, we suggest to use that car box. The indexes in water is pretty simple. It's water index 1 and 3. Those are the ones that we are using. They're very highly correlated. So actually, probably one will do the same work as the other. But we can put those of them. In the nitrogen part, I don't know, I'm not the specialist there, so the people that is the leaders of the nitrogen groups in wheat and barley will need to make a decision there about their indexes. So Kevin Smith and Clay Sneller probably need to make some decisions there. In water, as I said, it's pretty simple. I think that we will stick with those water indexes that seem to be doing a good job. There's already literature on them, so there are things that CIMMYT is also using, so we'll make data comparable with their studies. So I think that for that, if you want to have some of our data to start playing, just contact Tyson and we can send you the data we have, so you can start seeing how it incorporates at T3. I think that if possible, it would be nice in T3 to have all the spectrum data and then the indexes, but having all the 12,000 points from the spectrum data will allow people to go back into the data and reanalyze the data for any index they may want to look. So if it's not a huge demand on memory space for T3, it would be nice to have all those samples from each plot. But I don't know, that's something that you will need to tell us. If it's impossible, then we will store only how many points for each?
2048, I think, 2000.
2000 for each point. So you will, that's something that will depend on how difficult it will be for T3 to store that let's say thousands of plots with 2000 rows of data. But if not, we can save just 20, 30 indexes, and that will not be very demanding. Okay, so
And the answer to his question is no.
do you? Yeah.
Okay, so also David asked if we use SpectraSuite for any of the analysis. We have not really touched that program at all. It's much simpler to just do everything in Excel, since we're not necessarily doing the things that SpectraSuite was designed for. So we've mostly been doing everything in Excel and SAS. So some other things about CropScan versus JAS. One of the things about CropScan was it was designed specifically for fieldwork, for doing exactly what we're doing. But on the other hand, the technology is about 20 years old. This has its ups and downs. On one hand, there's a lot of documentation. For the JAS, we're really the first people trying to do this using Canopy Spectral Reflectance in the field. So we're developing a lot of the things. The CropScan has already done all of that. They've done all of the experiments and established everything. They're also a small company and they have good customer service. We've had some problems with Ocean Optics, but we're kind of making our way through it. On the other hand, the CropScan is large and it's cumbersome to work with. The JAS is nice because it's so tiny. It's really easy to move around and stuff, but the CropScan is quite a bit bigger. It's got wires going everywhere. It's just kind of unwieldy in the field sometimes. But one benefit is that you can easily use a CropScan with one person. It's just a lot of stuff to carry. One big problem we were having with the CropScan is that the pole is meant to be held at an angle rather than straight up and down like our JAS poles were. But this causes problems because of the spacing of our plots. They're planted very close together. So if we actually try using the pole as it was designed to be used, the pole is like halfway in the plot behind us. So it causes problems with that. We had to kind of just hold the entire pole up over our plots when we were collecting data with it the first time, only to find that we didn't actually collect any data.
Maybe. The other advantage that the CropScan has is because they are fixed wavelengths, they have optimized the integration times specifically for each of those wavelengths. So in the JAS, you have the problem that you need to use a single integration time for all the wavelengths. So none of them are optimum for a specific wavelength. So the JAS has that additional advantage. So we will explore it and see if we can use, or if it would be more friendly for for breeding operations that require a less sophisticated operator. I think that the chassis is working very well in our hands because, well, Tyson has the brains to do all the programming and fix all the programs and things that needs to be fixed there. And I think it's really more flexible and enticing for younger people to use, but maybe the other one still has a place for a less sophisticated technician or field people operating it. So we will explore it, but we don't have much experience yet.
And that's about it. So thank you everybody for attending our webinar session. If there's any questions, go ahead and type them in the box.
Sure.
Is there anything else you want to do?
No, thank you. Thank you. Thank you. Thanks. Okay.
Okay, well, yeah, if anybody does come up with any questions later, I think this was recorded so you can go back through here. Maybe we can also post up the PDF so you can look at that stuff. But please, anybody that's doing this, go ahead and look at the forums, use those. If you have questions, post them up there. That way we can answer them and everybody can see the answers. So we don't have to keep sending emails back for the same things over and over. There's a lot of stuff up there already. I've uploaded all of my scripts, the Pro scripts, the Jazz scripts, and instructions on using all of those.
And I will ask Tyson to set up one file that will call standard parameters that will be at the beginning our parameters. And then we will, those of you that oppose any of those parameters, send your proposal and explanations, and we will keep updating that standard, but at least we will have something that we can call standard parameters to start use. So look for the file that will say called standard parameters.
Yeah.
Great, thanks Tyson. And George?
Yep.
And I included, for those of you still on, I included my email there.